Here we see two objects, object A and object B, or more. Let's talk about them as systems. So we have system A. System A includes the cube or the square, the books, the table, and the earth. Even though we don't see the earth in the picture, we do infer that the earth is there because we we're going to talk about gravitational force acting on the object. So the interaction between the Earth and the object is what um, creates that gravitational force. So we have the object, the books, the table, and the Earth. So that's on the left side on system A. On system B, we just have the object, the table, and the Earth. Now, do both of these objects have the same potential energy, and why or why not? Well, in from one perspective you could say that no, because if we think about potential energy as the potential to turn into kinetic energy, the potential of the object to fall, object B can fall farther than object A can because object A has these books in the way. So if you let go of object B, it's going to gain more kinetic energy before stopping than object A is. So, object B, the way that we're going to be talking about potential energy in this class, we would say that object B has more potential energy than object A because it has more energy that can be turned into kinetic energy. If you let it go, it's going to fall farther, and if it falls farther, it's going to gain more velocity. So, what is potential energy? Well, potential energy is, as I suggested in the last slide, potential energy is, in this case, it's energy that can be converted into kinetic energy. It's the energy of position. So, if something has kinetic or something has potential energy based on its position or its shape, usually it's positioned in some kind of a field, a gravitational field or an electric field. Here we see we're just talking about gravitational potential energy here. So the gravitational potential energy of this block has a mass of 1, and in A and B, we'll just say it has a height of 1. So if it has a mass of 1 and a height of 1, the distance above the ground is the height, or above whatever object it's going to hit. So it has a mass of 1 and a height of 1, then it has a potential energy of 1. On image B, we can see we double its mass. It has a mass of 2 and a height of 1. So now if it has double the mass, it has double the potential energy. So it has a potential energy of 2. Remember, in kinetic energy, we saw that mass and velocity had a different amount of impact on kinetic energy. Now let's look at potential energy. Let's look at the other factor other than mass. Let's look at the height. In image C, we've doubled the height, but notice we have the same mass of 1, height of 2, but the potential energy is only 2 bars. We still only doubled the potential energy. So potential energy is not calculated like kinetic energy, where you have one factor that has a much bigger impact than the other factor. We have really 3 factors in potential energy. We have the mass of the object, the height of the object, and then the thing that we don't see here would, because it's pretty much affects everything else, everything universally. It's the impact of the gravitational field. So when just like if a coach tells an athlete, you have potential, or that means that you have the possibility of future success. Something with potential energy has the ability to move in the future. Now, near Earth's surface, we've already learned that the acceleration due to gravity is always the same, or pretty close to the same. Varies by only a tiny amount. Whether you're in Death Valley or up on the top of Mount Everest, you really haven't traveled that far from the center of the Earth. You might feel like it if you climb Mount Everest, but You- you're not far enough to make a significant impact on the acceleration due to gravity. In fact, we even saw it up on the International Space Station. The acceleration due to gravity is not that much different than it is on the surface of the Earth. And near the surface of the Earth, the acceleration of objects uh, is given by the small letter g. G equals 9.8 or 9.81 meters per second squared. That's the acceleration due to gravity. That means that the force pulling down on an object is mostly determined by the object's mass. It's not determined by gravity. I mean, the gravitational force changes with respect to the object's mass. So a change in height doesn't have a big impact. It because it doesn't change a change in height doesn't change the gravitational force significantly. So it's really only the mass of the object that changes the amount of energy, potential energy. So, as stated earlier, potential energy is related to how far an object can move relative to a zero position. Now, we can define that zero position as the ground. When we saw the object dropped onto a bunch of books, we could define the zero position as the top of the books. The zero position is defined by you when you define the system. Here's the equation for potential energy. Make sure you write it in your notes. Potential energy is equal to mgh. It's a very easy equation. There are no fractions, no exponents, nothing. So m stands for mass. G is the acceleration due to gravity, which remember is 9.81 meters per second squared. And height is the distance from the zero position. So the zero position can be the ground. It can be if you're lifting something above a table, the table can be the zero position. You define what the zero position is based on the scenario. You may also see an equation for potential energy written like this: capital U equals mgh. U is a symbol that's used frequently for potential energy. In our textbooks, they tend to use PE, but if you see U, you'll know what it is. U is potential energy.